Okay, thank you. Let's get started. So my name is Kareem Mastoud. I'm the Manager of International Projects at Premier Corex. Thank you for joining the session with us today. If this is your first time, welcome. If you have joined with us before, thank you, and it's great to have you back. Today we are joined by Jules Reed. Jules is our Vice President and Group Technical Director at Premier Corex. He will explore the role of core analysis in validating CO2 storage and supporting CCUS projects. Jules' topic is very, very interesting. Before we complete the introduction, just a few housekeeping rules. Please use the Q&A panel to submit any questions that you have. We will answer at the end of the session. The session is being recorded. The session is being recorded, and and we will share the recording afterwards. Okay. The session is timed for about 45 minutes and Q&A at the end. All attendees are muted during the webinar, so audio is not enabled. Okay. So Jules, a bit of intro about Jules. He's the co-author of the book Core Analysis Best Practice Guide, which is the textbook on core analysis. He is former president of the Society of Core Analysts, currently sitting on its technical committee and peer reviewer for the technical journal, including SPRE and GPSE. He is expert in most aspects of core analysis, with particular insight on wettability, capillary pressure, relative permeability, and EUR. Okay. Jules, over to you. I'm going to relinquish control, and if you can start your session. Thank you.
Okay, thank you, Kareem. I'm going to just verify you can hear me.
Yes, we can.
Excellent. Excuse me. So, as Kareem said, today I'm going to look at CO2 and calling it supercritical for de-risking carbon storage testing. I'm going to use the 4 items that we put out for going through this topic today. So first, looking at what is supercritical CO2 anyway. I've put these in maybe a slightly different order to what we sent out. Then look at core testing for storage and for seal units. Ask the question, is a full suite of analysis always necessary? And then look at, as we described, look at some of the common pitfalls in laboratory analysis. So I found this a very useful and very interesting video. You can find this on YouTube, courtesy of J. King Research Group. It's been on YouTube for about 15 years. And it's a tube analysis looking at water and CO2 under different pressures. And I'll start the video here. Oh, thanks. And what it starts off at, it starts off with just water and CO2. And this will be gaseous CO2. We're not above the supercritical point of CO2. So if I just go on one, here's a phase diagram of CO2. So that around about room temperature and room pressure, CO2 is a gas. So room pressure will be 1 bar or 1 atmosphere. They're almost equal, not quite. And about 273, 275 Kelvin, which is equivalent to about 293 actually Kelvin, which is equivalent to 20 degrees centigrade. So you're here, CO2 is a gas. Now, what can happen is we increase pressure. It's still a gas, but at some point, depending on the temperature, it becomes liquid, and so you begin to condense some CO2 into a liquid. If you continued with pressurizing at some point, again at the same temperature, you'll actually begin to get solidify. Now you'll all be know solid CO2. We call it dry ice, where we've reduced the temperature, and so we begin to get solid CO2. But as we for every element or molecule, you'll have this phase diagram: a solid, liquid, gas, and this is generally what you get taught at school, 3 phases. But actually, in all these elements, there's a 4th phase, and that's supercritical. And every molecule will have, or every substance will have a critical point or a supercritical point. It will have a critical temperature and a critical pressure. And if we're beyond the critical temperature, that you'll always be in some form of a compressible fluid phase. If we're above the critical pressure, then you're going to be in some form of the liquid phase. And so what happens when you're beyond both critical pressure and critical temperature? You're in this sort of in-between phase, where it can sometimes act a little like a liquid, but also acts like a compressible fluid or gas. And so let me restart this video. So initially starting with water and just gaseous CO2, and we're injecting CO2 gas. And as they inject the gas into this sealed system, you can see the pressure is continuing to rise. Temperature is roughly staying roughly constant. And so we begin to, at this pressure here, you can see we begin to get 2 phase meniscuses or menisci, until at some point, just here, where we've paused it before, you've got one meniscus here, which is the water phase below it, and then liquid CO2, because we've gone past the point where the pressure where you can have liquid CO2. So some of the gaseous CO2 begins to convert into liquid, and then on top you've got this gas CO2. So you've got 3 phases in here: water, liquid CO2, and gaseous CO2. And as we continue this process, we can now look at increasing the temperature. And as the temperature increases, you can see that the phase, liquid phase, begins to disappear, and you begin to get it begins to mix with the gas, and you begin to get a single phase. That was it, just changing the angle so you can see the single phase of single meniscus that's in there. And so you get to this stage where you've just got where you've only got 2 phases in here. You've got water and supercritical CO2, which is neither a gas nor a liquid. It's a single compressible and slightly denser than gas phase. And then what happens is we begin to reduce the pressure. You begin to get this cloudy look as the CO2 liquid, or you begin to condense. It's this mixed, what looks like a mixed phase. It then clears. This video is not working quite as expected. You get this mixed phase, and then at some point, and this will be around about 120 psi here, just there. You've got water and basically gaseous CO2 above, because we're above the critical temperature, but a lower pressure, 404 psi. And so we're in the gas phase of CO2 again. And then at some point, you suddenly see gas here beginning to appear as you continue to decrease the pressure. So you've reached the bubble point of the water. Now, the water initially had no gas in it. And so by bringing gas and bringing the CO2 in contact with the water and pressurizing, this is the same as what happens in Coke bottles. Some of the CO2 is transferring into the water, and so that when we depressurize the water now, we're getting CO2 coming out of solution by the change of pressure. So that's just a quick introduction about supercritical CO2, and it's all controlled by temperature and pressure. So going on to core testing for storage and seal units. Well, the first thing we would say is that many things are the same, some are slightly different. The things that are the same, you still have a subsurface system where you're going to need to characterize and understand what that system is about. Understand the properties of the system, understand the different layering, the different permeabilities, porosity. There's the standard characterization of the system, of the reservoir, or now we would call it a storage unit. The standard properties of that storage unit, so that you can begin to calculate, one, the volume that it can take, and you can inject, and understand where the CO2 plume is going to migrate. So you, again, just the same as standard reservoir properties. Of course, CO2 is going to inject into the most permeable portions first, and travel through the most permeable layers more rapidly and more readily than the the less permeable layers. But one of the things to potentially is a bit different to than one of the things that is slightly different is, so far in normal hydrocarbon systems, we've not been so interested in the seal. So quite often the seal has not been cored. We don't know if there's, we are potentially uncertain of some of the properties of the seal. And so you're going to need to study the seal capacity, the strength and the threshold of that seal, looking at things like seal integrity and potential failure stresses, but also looking at what happens when it's exposed to CO2. CO2 we know is particularly together with water creates carbonic acid. And carbonic acid is going to interact with certain minerals and certain components differently to how the formation water alone will interact with it. And that's not just going to be this case in only the seal, it's going to be the case in the reservoir, the storage unit as well. So the analysis in the storage unit, you need to understand storage capacity, and the injection capacity, so how rapidly and how quickly you can inject. That will require the petrophysical characterization, maybe a petrographic characterization of XRD, to allow you to understand things like the exposure properties. So what's the impact of CO2 going to be on those properties? So that is another thing that is going to be slightly different to most hydrocarbon systems, is how does exposure to CO2 impact the storage unit and the seal properties. And so you're going to require things like the petrophysical properties, such as capillary pressure, maybe understanding pore size distribution, particularly looking at threshold entry pressure, and looking at those properties as a function of other the measurable reservoir properties, deriving things like effective permeability. So understanding relative permeability, effective permeability, understanding the absolute permeability of the system are going to be necessary. And then relative permeability, and maybe not just relative permeability, but the impact that other processes might have on those properties as well. So as you inject CO2, you are injecting potentially a dry gas or a dry supercritical fluid, as we saw in that video. Some of the CO2 is going to go into the water, but also some of the water will be dissolved into the CO2. Some of the water will evaporate into CO2, and you will have a humid or humidified supercritical CO2 fluid going through the system. And so around the wellbore region, you may have drying out of the initial water saturation, and then potentially precipitation of those components that are taken as either water or CO2 move through the system, precipitation of salts, and that could have an impact on relative permeability. As well, depending on the process that's going to happen in the reservoir, you could see some spontaneous inhibition of water, and that's going to impact. So you may need to look at the hysteresis effects of relative permeability. So all of these things are things that you may need to look at, as well as capillary pressure. So understanding as you inject CO2, how under the different heights and pressure regime, the CO2 and brine will situate themselves. And there are various methods of measuring that. One of those is by centrifuge, where we spin the samples, applying different forces for different spin speeds, either in drainage or imbibition mode. And then converting that, it's more a complex, or potentially a complex differential conversion from the average data that we obtain into a realistic capillary pressure. Another method is the porous plate method. Porous plate could be measured simultaneous with electrical data. Whether you need electrical data is a question. The only reason you may need electrical data is if you're going to be monitoring saturation changes by using electrical logs. If you have a monitoring well, those could be loaded either as separate systems or could be loaded into their own core holders, where we can control temperature and pressure, and potentially capillary pressure as well. That's a very difficult process to control with supercritical CO2. So it's some of these analyses are challenging and difficult and very long term, and then because they're challenging, much more expensive. So it comes down to budget and time, as with all things, of what method you want to use. It's important to take things to completion as well, to try and ensure you've got stabilized production at each pressure you're applying, so that you get a more accurate saturation and capillary pressure correlation. Also, relative permeability. We want to look at relative permeability. There are a number of different methods. It's going to be slightly different to a standard relative permeability process, and unless you've been used to doing primary drainage relative permeabilities, where there's always then a question of, well, what is primary drainage actually, RelPerm actually going to tell you about the reservoir from its point now? It only tells you how it got to its current process in a hydrocarbon. But if you're injecting into a virgin aquifer, then you're already at saturated formation, saturated with formation water. So just measuring the current properties and current water permeability, and then injecting CO2. Now, the whole that you have to consider equilibration of fluids, because relative permeability is an immiscible process. And as we saw in that video, in increasing pressure by injecting CO2 into that cell, there was transfer of some of the CO2 molecules into the water. And if we don't equilibrate your fluids, if you don't mix them and ensure that your water is saturated with CO2, and likewise your supercritical CO2 is saturated or humidified with water, then you will begin to have those transfer effects in the test. So it's important to equilibrate your fluids before you run a CO2 flood, if you're going to calculate what the miscible or potential miscibility effects may be. And then quite often you see I've put here centrifuge to SWI. Well, actually at the end of this test, you're probably going to get to some kind of remaining or residual water, not immobile water. And the centrifugation could take you to lower SWs. We'll come on to why that might be. Same with steady state testing. Again, it'll be the same process of from saturated, measure your permeability, and then simultaneous injection of supercritical CO2 and water. And again, a need to equilibrate fluids. And then maybe centrifugation at the end to get to SWI. Geomechanics. Understanding the geomechanics is going to be an important process. We're going to be pressurizing up a system. Either it's a virgin system when you're pressurizing and you want to understand what the impact of pressurization is going to have, or it's a depleted reservoir system where you've removed the pore pressure and you're going to start increasing pore pressure again. And so you're going to want to understand the hysteresis effects of pressurizing, depressurizing, or depressurizing and repressurizing that system. So looking at both static and or dynamic measurements, that's performed in a test cell like this. This is an example of a sample loaded to one of our load cells. Of course, it would be surrounded normally, but you have your monitor system around 4 different points of the circumference to monitor changes in strain as you stress the sample. So monitoring any diametric or radial changes, as well as monitoring any axial changes as you stress that system. And so from that, you can obtain Young's modulus, Poisson's ratio, the bulk modulus, your failure envelope. So we can take samples up to the yield point, beyond the yield point into the plastic zone and to the failure zone, to look at that whole stress regime and give input to understand the seal capacity and the seal integrity from a geomechanics perspective. The other part of the seal unit that's going to be necessary or potentially necessary to consider is the threshold or entry pressure. And that's the point or the pressure at which CO2, supercritical CO2, will begin to inject into the seal and push through the seal. And that's going to be equivalent to usually the largest pore space that is accessible to the CO2 or is contacted by CO2. And very often that's a function of permeability. We know that permeability can be correlated to a pore throat size. Well, the entry pressure is also correlated to a pore throat size. So we would expect that there'd be some kind of correlation between entry pressure and pore throat size. And this is showing, in this particular case, mercury injection data and CO2, supercritical CO2 brine data. Now, one of the things to note on here is that the permeability here was not permeability to gas for the brine system, but permeability to water. And so that can be lower. It can be significantly lower. I'll touch on that a little in a few minutes as well. But the mercury injection data, you're going to need to convert to CO2 brine by using the Young-Laplace equation, knowing IFT and contact angle for mercury, knowing IFT and contact angle for your CO2 brine system. So the CO2 brine is going to be generally a more accurate process, or more accurate measurement of the system. You're using the actual fluids, whilst air mercury is not using the actual fluids. But MICP can be very useful. You get generally relatively quick data from MICP and a lot of data. You get pore size distribution, entry pressure, and it's relatively cheap. Whilst the CO2 brine, or supercritical CO2 brine, can take considerable time, and it's much more expensive because of the type of testing and test time that's necessary, and high-end equipment that's needed to get into those supercritical systems. And there are a couple of ways of measuring that in a supercritical brine system. One is the step method, which could take significant time just on its own. Or there's a method that we tend to use ourselves, which is a continuous pressure ramping, where we have a system, we know the calibration of the system, of what volume is required as a function of the pressure or time, as well as ramping up the pressure in just a constant ramping mode. And then when we do this in a system with a sample, we can see the point of inflection where we begin to see additional injection outside of just what it requires for compressing CO2 into the system. So, is a full suite of analysis always necessary? Well, that depends what information and what data you already have, or partly depends on that. It depends on your objectives and what are the current unknowns and the current goals of a system. What information do you need? And so balancing what you know and what you need versus what needs to be measured. And some of that is going to be controlled by the uncertainties. So a lot of log data can give you a lot of useful information, but there are the potential more errors in log data compared to core data. And so you can get a reasonable understanding of data from logs, but there are certain additional data or confirmation and reduction of uncertainty that comes by using core. And we can calculate that as the values here were calculated on understanding of about $50 per ton of CO2. and the requirements to inject CO2 to say 3000 psi at 70 degrees C. So injecting from roughly atmospheric conditions, or however it's transported to the injection site, injecting and pressurizing up to 3000 and then heating as well to 70 degrees C. These are the differences in costs based on that reservoir system that is 1 mile by 1 mile and 200 feet thick. And so there can be significant reduction in uncertainty from performing the core analysis. However, core analysis takes time and is an additional cost, and often these your CO2 projects or your storage projects, or you have budget limits and time limits, and you need to look at the balance of that and look at what value you're going to get from the CO2, or understanding what is necessary from local regulations. And local regulations and local government requirements differ from country to country. So you will need to understand what your local requirements are. So it partly depends what you know. And in virgin aquifers, potentially very little is known. There may be little or no core, which means you're probably going to need to acquire core, and will probably require all of the fundamental characterization, as well as some of the more advanced testing to understand the dynamic properties as well. If you're in a depleted hydrocarbon system, there is already a lot that will be known, and maybe lots of core, but potentially nothing known about the seal, and maybe little known about the geomechanics of the system. And so there will be different levels of investment or analysis required depending on what your system is and what you know. And finally, what are some of the common pitfalls in laboratory analysis for CO2, supercritical CO2 and brine systems? Well, one will be using standard values, because if you don't have data, you don't know what you'll be going to literature and looking at standard systems or analog systems. There's also the fact that you are assuming absolute values for certain things. I'll come on to that. There are also, if you're doing dynamic systems, capillary end effects, which, because we're using a very low viscosity as a fluid to inject, so supercritical CO2, yes, it's denser than gaseous CO2, but it's still not overly viscous, and so you have a high mobility ratio. And so you begin to get capillary end effects, and they're larger than in maybe some certain water oil systems. Also, unstable productions, potential for unequilibrated fluids and uncertainty from unequilibrated fluids, and also increased fines or sensitivity issues. And I'm not going to go through all of these. There are also potential additional ones to these as well. So what it requires is study to look at what your system is, how it will interact with CO2 and brine, how those interact together, the fluid compatibilities, and then trying to look at what you're going to expect to see, and maybe beginning to investigate those aspects that are going to cause the biggest uncertainties in the system. So I'll go through some of these. First one is beware of typical standard values. If you've been involved in petrophysics for any length of time, you'll know this table. It would say that a gas brine system, and very often most people thinking CO2 as a gas, and a gas brine system at reservoir conditions, typical value of 50 as an IFT, 50 dyne centimeters or millinewtons per meter. And the contact angle is 0. And so when you do the cosine of contact angle and sigma IFT, then you get the overall sigma cos theta is 50. However, that's changing. So these are water droplets in supercritical CO2 under different conditions, different pressures and temperatures. And so we've got the interfacial tension above there. We can see at lower pressures, high interfacial tension. As you increase the pressure, you reduce the interfacial tension. At the same time, so we consider a water droplet in general to be 0. Now, what this looks like if it was 0 degrees contact angle, you wouldn't see the water droplet. It spreads so far onto the surface that it spreads off the visible range of the equipment, and you can't actually measure an angle. But this is one at increased pressure. We begin to see, and at supercritical conditions, we begin to see a contact angle of the water. So it's no longer, it's still water wet, because these angles are still what would be considered water wetting in an oil water system. So normally a standard value for oil water would be 30 degrees, but it's no longer a gas water system with 0. So needing to understand the change, potentially needing to understand the change in contact angle, and also particularly in interfacial tension. Because if you were using 50, but you're actually 28, that's going to be a twofold error in your capillary pressure calculations. And so these are some measurements we made from 25 degrees up to 150 degrees Celsius, looking at the change in with pressure for each of those. This was also there's a paper then by Gerold and Korani in 2022 where they looked at interfacial tensions change and this is the relative change from the starting point of each of the of CO2 water at different temperatures. So that's quite similar to here. What rather than it being normalized or the relative change, I'm showing the actual values here. So you can see as you increase temperature, you actually decrease the starting or the initial point that your then relative change is based upon. And so and then also pressurizing the system and changing contact angle. And this was from a paper by Gava et al, where they were showing by pressurizing the CO2 brine system for different rock types, you may have different contact angles. And so understanding those systems may be quite important to understanding capillary pressure in your system. And also when we're thinking about capillary pressure, the way that we tend to think about it is using a single interfacial tension for the whole of the capillary pressure curve. And for most liquid systems, that's okay. So this is from Hassan et al. In 1953, This one here is for benzene water system. This one for octane. So these are liquid hydrocarbons. And if you were saying going from, say, 700 psi, you're say, let's take this one at 60 degrees, you're going from 31 dyne centimeters to 30.5. That's very little change or alteration. If we take this one at 60 degrees as well, say from 700, or even from zero, at zero you're at 47, reducing at 3000 psi to 45. So it's a difference of 2 dynes per centimeter, which for large part is not a large change. And so it has very little impact, or potential impact on capillary pressure calculations, as long as you're using something as an average of the liquid-liquid interfacial tension. However, when we get into CO2 brines, I've gone past it. When we looked at the CO2, we can see large changes, and so that's going to have a large impact. But at low capillary pressures, that's going to be a different interfacial tension than at high capillary pressures. And you can't just use a single interfacial tension. You can't just do it as a one-time calculation. You have to actually iterate on the data until you begin to get stabilized values, because the known pressure is the air mercury pressure with known properties and virtually relatively unchanging properties of air mercury, but the properties of the CO2 and brine are changing as a function of the pressure being calculated. And so you have to calculate that one time, redo the calculations for each of them until you begin to stabilize your calculations. And this is the potential difference. So this is the actual air mercury data. This is it if you were just calculating gas water at 50. And for this particular system, if you'd done this at the first iteration, this is the curve that you had got. And at the final iteration, it's close to the gas water at 50, but it is still different, and very different from your if you were just assuming that first single IFT value. So there can be a significant difference. So let's look at absolute values. Literature tells you that absolute permeability is absolute independent of the fluid being used. Well, quite often we see that a slight difference, but everybody knows that gas, you get different permeabilities depending on the pressure being applied. And so we convert that into Klinkenberg permeability. And the supercritical CO2 here converted to Klinkenberg supercritical CO2 for compressible fluids. We see that all of these, once converted to Klinkenberg, are relatively similar. But then the water permeability for this system, which has quite significant clays present, is much lower, and the liquid CO2 was in between the water and the Klinkenberg. Now, this is going to be important when thinking about RelPerm, because what do you base your relative permeability upon? If you base it on water, which is the current 100% saturating system, then you could have the CO2 calculations or RelPerms above 1, and certain simulators won't allow that. Capillary end effects. These are modeled, but we've seen these from in situ monitoring in the lab. That depending on the length of sample you use and the rates that your injection rate you're using, you will see this changing saturation as a function of length in the sample. And even at 50 centimeters long, you still have this large capillary end effect. And this is the impact, or the sort of impact it can have on relative permeability. So you need to understand your capillary end effects and correct the data for the capillary effects. And that's referencing back to earlier when I was saying the need to understand capillary pressure and how that is impacting dynamic processes. And then unstable production, if you don't allow stability, the green here is where you've just done this for say 12 hours per step, whilst the whole test here has gone on for I think more than 3 or 4 weeks it took to stabilize different flow rates or different rates here. The difference between those two production scenarios looks like this in terms of capillary pressure. And if you calculate what that would be, that's a significant error in potential storage capacity. So it becomes a significant, it's significant to allow testing to stabilize long enough. And the last one is, it's about fines migration or potential additional sensitivity to fines migration or being sensitive to clays. This is a test using formation brine where there was low fines migration, but when using carbon dioxide, one sample in particular had the potential, a possible potential for higher sensitivity or damage because of the fines migration. And for long-term injection, all of these samples saw long-term potential degradation in injectivity or permeability. Okay, so I think we're almost out of time, so we've got a few minutes for any questions, and I'll hand back over to Kareem to manage the questions.
Thank you, Jules. That was quite interesting and quite informative as a great presentation. We do have some questions from the audience. I think the first question we received was somebody was asking about any paper books to talk about these lab tests for the subject. He has read the book, says it's since 2015, and therefore was wondering if there's any recent literature.
Yeah, there's quite a lot of literature out there. I'm not sure how many papers I have on CO2. I've been using CO2 for enhanced oil recovery for over 20 years, and so there's a lot of information known about CO2, and usually if it's in an enhanced recovery system, you're at temperature and pressure, so it's supercritical. And yeah, the library I have, I'm just looking to see how many papers I have on this. Yeah,
So I think the gentleman
I've got at least 64 papers on this. Okay. So yeah, there's significant literature out there, but there's not a single. Well, I think there's a good book by Philip Ringrose. Would be if there's a book out there to get, that would be one I would recommend.
Okay,
but it's not specific to. Sorry, it's not specific to all of these testing.
Okay, so I think the question really meant is if we could we build the whole process of experiments to study. I think that's the purpose of the question. Okay, so I think maybe a literature encompassing all the testing protocols, or maybe a workflow.
For that I would suggest, because the workflows are different depending if you're in if you're going to be injecting into a depleted hydrocarbon system, or if you're injecting into an aquifer. If you're injecting into an aquifer, you probably the change in interfacial tension, you're already at quite high pressures, and you're going to be increasing pressure, and so the change in interfacial tension is potentially not that significant, or not as significant as if you're injecting into a depleted hydrocarbon. In a depleted hydrocarbon system, there are other uncertainties. So as I said at the start, what actual testing you need is going to depend on what your objectives are and what the system is and what you already know about the system.
Okay. Thank you, Jules. So we have another question. So in the absence of available core, considering cost savings, what are your thoughts on using cuttings as a substitute, also as a supplement?
Yeah, you can get a lot of information out of cuttings. So a lot of good, particularly some of the lithologies like XRD, XRF. If you've got cuttings that are large enough to see pore space, you can begin to get pore space out of there, and porosity, potentially permeability calculations from the pore, from building a pore network or digital rock. Excuse me. However, you're not going to be able to do dynamic properties, and so it's limited, more limited with what you can get out of the cuttings. The interaction of CO2 and onto the minerals, and the potential change in mineralogy from carbonic acid could also be tested on cuttings.
Thank you. Another question is, many thanks for the nice presentation. For CO2, O'Brien, relative permeability measurements, do you consider the steady state method more reliable than the unsteady state method? In particular, how do you account for capillary end effect, CO2 compressibility, and dissolution effects when interpreting the data set?
A very good question, and a very far more challenging than you would actually think. And it's all because of equilibrium or disequilibrium effects. The CO2 water equilibrium is quite sensitive, so for you've got a couple of things you're trying to balance. Unsteady state, you can control you can do a low rate and then followed by high rates, where the differential pressure, because you use a low rate, is the differential pressure is lower in your initial flood, and then when you go to higher floods, the flow of CO2 is not so large, and so you can control the disequilibrium a little. With a steady state system, it depends if you're then with a closed loop steady state or an open loop steady state, where if you're open loop, you've got limited volumes of fluid, and so the rates that you have to go to try and reduce capillary end effects. So we've done this testing in up to almost 30 centimeter long samples. You still, as you saw from the simulations, you still see the end effect. Going up to 30, 40, 50 cc's per minute, you still see an end effect. But at 30 cc's or even just 10 cc's per minute, depending on permeability of the system, your differential pressure is large, and so the impact of equilibrium or uneven equilibrium, because you've got high pressure at one end of the sample, lower pressure at the other end, that disequilibrium causes significant challenges to the the phase properties. And so you're no longer an immiscible system. So you have to control differential pressure. And so steady state would generally, you get a wider distribution of saturation, but you get it's much more difficult to control the equilibrium of the system, and this is quite a volatile system.
Okay. Thank you, Jules. So the next question is, thanks a million for the valuable information. My questions are, number one, how significant is wettability alteration during long-term CO2 exposure? And do you believe conventional scale workflows are still sufficient for reliable prediction? So that's question number one. Number two, in your opinion, is the industry currently overestimating the confidence of laboratory-derived CO2 storage predictions?
Okay, the first one, how significant is the change? Well, in terms of wettability, it's still water wet. So and we, you're going from, if you look at the contact angle, you're going from 0 of a gas lit water system to maybe 20 to 30 degrees. That's still water wet, and it's still strongly water wet. If you were to take a cleaned water wet sample with a liquid laboratory oil hydrocarbon, you would get around about 30 degrees, and it would be strongly water wet. So wettability is changing. It is slightly less water wet than the 0 degrees, but it's still water wet and strongly water wet. So that's the first thing. And what was the second question there?
The second question, in your opinion, is the industry currently overestimating the confidence of laboratory-derived CO2 storage predictions?
It depends how it's being done. I think there's a lot of literature that I think the biggest uncertainty is in relative permeability. There is literature out there that says there's no impact on relative permeability, whether you use it as a gas liquid system or you do it as a supercritical fluid liquid system, or supercritical CO2 water. My experience and there's literature that says it is different, and my experience tends to be that it is different. There is a slight shift in the relative permeability.
Okay.
So whether we're over it, I think it depends on the test itself and the data itself, and how competent and understanding the testing has been, and then how well it's being used as well.
Okay. All right. Thank you. So next question is, why does absolute perm to liquid CO2 differ from water permeability?
So this will be, if you go back when I began in the industry, absolute was absolute. This is what we were told. So absolute permeability to gas is the same as absolute permeability to oil, is the same as absolute permeability to water. And then we began to see differences in water permeability in particular, and water permeability being sometimes drastically lower than the gas perm or the Klinkenberg perm. So sometimes up to 10 times lower or more. And when I started looking into the potential of other papers out there, well, there are papers going back to the 50s of people showing water permeability much lower than gas permeability, excuse me, and usually because of the presence of clays and the fact that the water is interacting with the clays differently to how gas or oil interact with the clays or don't interact with the clays. And this is the reason why what you tend to see is where you've got large clays present, there's a large difference in the water permeability. Now, what we do see is CO2 is partially wetting, as particularly as a liquid, and so CO2 as an acidic molecule is interacting with the clays as well. Now, it's maybe not interacting with the clays as much as water is, but there is interaction. But what it does do, and there's literature out there that tells you that CO2 weakens the interlayer between clays, and so has the potential to fines migration. So CO2 is interacting with clays, maybe as a slightly weaker force than water, but I think that's why the liquid CO2 is you're seeing this difference to water permeability. So understanding the clay system is important to understanding your flow systems.
Okay, thank you, Jules. So I have another question. Could you share a whole process of experiments to study this subject? So I think it might be the same gentleman looking for a workflow.
Well, so workflows, like I say, that depends on the system. You would have to put it together depending on what your objectives are. And I would always suggest coming to a laboratory and discussing with the lab what is required and then designing the tests suitable to your requirements.
Okay. All right. Thank you. So we have another question from one of our regulars. So how sensitive electrical properties measurements would be when samples are saturated with liquid CO2 or supercritical CO2?
That's a good question, and I don't know. I've not measured the electrics of that, but it maybe deserves some research into that. Maybe get some of the universities to look into that question.
Okay. Thank you. So continue with more questions. So question regarding capillary pressure of CO2 at different state by considering
sorry,
humidity.
Kareem, I'm just looking at the time, and I'm aware people are maybe needing to go, and so are there many more questions, or are there some that we can answer offline?
Actually, we have 3 more questions. So if you are tight on time, we can respond offline.
So 3 more questions we can take.
Okay. Yeah. All right. Okay. So the question was regarding capillary pressure of CO2 at different state by considering humidity when water vaporizes. What will be its impact?
Sorry, can you repeat the question?
Regarding capillary pressure of CO2 at different state by considering humidity when water vaporizes, what will be its impact? Well, so I think the impact of water vaporization.
So
humidity.
The vaporization process is really only going to be an issue in the near wellbore area. As you inject, we'll call it, say, dry CO2, it's going to evaporate the water in the near wellbore region and dry it out. And basically, as you're injecting, you're humidifying your CO2. So when we look at this in the lab, we look at it more deep reservoir. Once you've got humidified fluids. The impact on capillary pressure is as you humidify a CO2, you're basically it's as you're pressurizing. So it really depends on the pressure of the system, because if you don't have immiscible fluids, so that means that there's basically no changing happening, then you're changing the properties. And if you're evaporating water, the capillary pressure is almost meaningless, because you're changing your saturation. Capillary pressure is a static term. So it's where the system is heading towards at the completion of an injection process.
Okay. All right. So another question: for CO2 injection into depleted gas reservoirs, how much influence does changing CO2 methane ratio have on IFT across the injection period?
And it's not just, it can be significant, I'll just say that. And it's not just CH4 or methane. It'll be other potential contaminants, we'll call them, or other gases that might be present. So if you're looking at flue gases, where CO2 is just the largest portion, well, you've got things like SO2 in there, which will reduce interfacial tension. You've also got, say, nitrous oxide in there that tends to increase. So it becomes complex. There is I think there's a paper by the International Energy Association, IEA, that looks at at least some of the properties of CO2 with impurities in there.
Okay, thank you. So thank you, Jules. So final question is, do you think the industry is still underestimating uncertainty in scale measurement for CCUS applications?
I think in the ones where you've got the scale measurements, like I said, depending on what's been measured and how it's been measured, potentially you've got a good set of data there. It's like everything. Just because you've got data doesn't mean that you should use it as though nothing is wrong. You always have to do your due diligence and your own checking and own quality control, thinking through whether it makes sense or not, researching as much of the information that's out there as possible before fully implementing. So you can't just take some data in isolation and use that data. You need to try and look at the breadth of different information available to you. Whether we're underestimating the impact, I can't say. I don't think that there's quite a lot of data out there, but whether all of that is being used, I think it's going to depend on the people using the data, where they've got the data from, and how those have been performed.
Okay, so that was a two-part question. So the second part is, which core-derived properties become most sensitive once CO2 enters the supercritical phase, and how does that impact storage security?
So capillary pressure as one, you saw the change in capillary pressure. The question then becomes, how important is that in your particular system? If it's a depleted hydrocarbon system, maybe it's quite important. If you're injecting into an aquifer, possibly less important. But it's important to know what interfacial tension is, because if you're just using, say, air mercury, you've got to have the correct interfacial tension to convert it from air mercury into your supercritical CO2 brine system, to understand how, when that's meeting the seal, how what pressure is that seal resisting? And outside of that, it really does depend on the interaction of CO2 with the particular components of your system. So and how it's injecting. So most systems are injecting CO2 in supercritical phase, or in the either as a gas, but transitioning to supercritical, where there may be fairly small changes apart from the capillary pressure and the slight change in relative permeability as well. But if you have a system with carbonates present, you've got potentially bigger problems than, say, capillary pressure, because you're going to have dissolution and precipitation problems.
All right. Thank you, Jules. Well, thank you. That was the last of the questions. It was a great session. Thank you very much for all that wealth of knowledge and information you're sharing with us. Appreciate that. So to all our audience, thank you very much for joining us today. We hope this has been beneficial for you. You will get a copy of the recording of the session shortly. Please follow us on our LinkedIn page for more updates from Premier Corex, and you can also see the recording on our YouTube channel. For our next session, we have a guest speaker, Craig Lindsay, talking about core analysis for understanding reservoir fluid saturation. Please tune in and register for our next sessions as well. Thank you all, and we hope to see you again.